Alright, these are some notes on section 3.4, and 3.4 is bringing up this idea of the fundamental theorem of algebra, which basically says that given any polynomial, there has to be at least one complex root, or complex zero. So basically that's just saying that it has to have a root. It can be an imaginary root or it can be a real root. So I give you this example. So when we look at this problem, x to the fourth minus 4x cubed plus 8x squared minus 16x plus 16, we have this polynomial, and when we put it in our graphing calculators, we will see that in our graphing calculators it is bouncing at the root 2. So remember we talked about when it bounces at a root that means that it has an even multiplicity or an even power. So we can tell from that graph that we're going to have an even power there. So when I do my synthetic division, I'm going to divide the root 2 out twice. So let me show you again. So when we look at our graph, and we have this in our calculator, you'll notice at the root 2 that it bounces off of the root 2. So again, so we do our multiplicity, we do our synthetic division with the root 2, and we end up with root 2 working, which we expected. Then I'm going to do synthetic division again with root 2 again, and again it works out. So now I'm down to, I've gone from an x to the fourth power to an x cubed power. Now I'm on an x squared power. So I have x squared plus 4 equals 0. And then I can solve that and I get plus or minus 2i. So my roots are going to be 2 with a multiplicity of 2, and then 2i and negative 2i. So here we have another example. So when we look at this example, when we put it in our calculator, we have 3x to the fourth minus 14x cubed plus 17x squared minus 4. When we look at our calculator, we can see a root of 2. So we're going to go ahead and divide that root out. Now our other two roots appear to be between 1 and 2, between 0 and 1. And then there's two other roots that appear between 1 and 2 and negative 1 and 2. So when I divide out my root of 2, I have to use my rational root theorem to come up with all of my possible rational roots. And 2/3 is the root that appears most likely to be the other root that I have between 0 and 1. So I'm going to try 2/3. And when I try 2/3, it does work out correctly. And so I ended up with either you can either think of this as a 3x squared minus 6x minus 3 problem, or you can factor out that 3 and think of it as an x squared minus 2x minus 1. That will not factor, and so I have to do quadratic formula. And when I do quadratic formula, I get 1 plus or minus the square root of 2. So 1 plus or minus the square root of 2 is about 2.4 and about negative 0.4, which is equivalent to what the two values were that I think I saw on my calculator. Okay, so the next example we have is what they call the conjugate root theorem, or the conjugate pair theorem. And what that says is basically if I have a polynomial, if I have a factor that is a complex or an imaginary root, a plus bi, then that means that a minus bi also has to be a 0. So here's an example, and when I look at this problem, I'm telling you that one of the roots is 2 plus I. So again, when I go to my calculator and I put this in my calculator, so I've got x to the fourth, x to the fourth minus 4x cubed, and then I have 14x squared, and minus 36x, minus 36x, and I have plus 45, And when I graph this, I don't see any real roots. So what I want y'all to do is go to your mode, and down here in your mode you can change your mode to A plus BI mode, and that will help us quite a bit when we're doing these problems. So I'm going to do synthetic division with the 2 plus I. I'm telling you that 2 plus I is one of the roots. So not only will we divide out 2 plus I, but we're also going to divide out 2 minus I. So when I divide out 2 plus I bring down the 1, I get 2 plus I. So on my calculator, 2 plus I times 1 gives me, whoops, I forgot to hit the times 1. Let's try this again. 1 times 2 plus I, you can't see it very well, gives me 2 plus I. Okay, so I get 2 plus I here. And then I take that and I subtract 4. So minus 4. And I get negative 2 plus I. And now I'm going to multiply that by 2 plus I. And I get negative 5. And then I'm going to add the 14. And I get the 9. And then I'm going to do 9 times 2 plus I. And I get 18 plus 9i. And then I'm going to do the minus 36. And I get negative 18 plus 9i. And then I'm going to multiply that by 2 plus I again. And I get negative 45, and that comes out to be 0. So I used my calculator to help me come up with this. It just makes it a lot easier than having to do the math by hand. Now I'm going to divide out 2 minus I, and I'm going to use this polynomial as my next root. So instead of having the 1 and negative 4 here, I have the 1 and the negative 2 plus I, the 9 and the negative 18. So I bring that down, I get 2 minus I, the negative 2 and the positive 2 cancel out, and the I and the I cancel out. Then I bring down put the 0 up here, and I get 9 minus 0 is 9. 9 times the 2 minus I is 18 minus 9i, and then those things cancel out. So again, I've gone from an x to the 4th problem to an x cubed problem, and now this is x squared, and when I do my solving, I end up with plus and minus 3i. So I have 4 complex roots, or 4 imaginary roots: 2 plus I, 2 minus I, 3i, and negative 3i. So it's something I wouldn't have been able to get on my calculator without knowing one of the roots. Okay, so here's another example. And this time again, I'm telling you that one of the roots is 3 plus I. So I'm going to work it out with 3 plus I. I bring this down. Then I end up with 3 plus I. Negative 8 plus 3 is negative 5 plus I. And then I did the multiplication over here this time, just so you could see how it multiplies out. So I end up with negative 16 minus 2i. Combine it with the 13, I get negative 3 minus 2i. Multiply by the 3 plus I, and I get negative 7 minus 9i. Add that 52 and I get 45. Multiply again and I get 144 plus 18i. Add those together and I get negative 54 plus 18i. Multiply these two together and I get negative 180, and then I end up with 0. So when I put, the next root is going to be 3 minus I, and again when I do the 3 minus I, it's much easier. So the i's are going to cancel out and I'm left with negative 2, and then I multiply that together. The i's are going to cancel out and I'm left with negative 9. Multiply those together. The i's are going to cancel out and I'm left with 18. And then multiply that together and again I get 0. So now I've gotten to a problem that is an x cubed minus 2x squared minus 9x plus 18. So I'm going to go to my calculator and I'm going to put that in my calculator. Okay, so what I did is I put the polynomial that I've gotten when I reduced it. Okay, and that's an x cubed over here. So I put the polynomial in as I reduced it, and now I'm going to graph it. And when I graph it, I can see that there's a root right here at -3, and maybe here at 2, and another one maybe at 3. So I'm going to divide out the -3, and that does work out. And then the other one I thought I saw was at 2, so I'm going to divide out the 2, and that one works out. And now I'm left with an x minus 3 problem, so my other root is 3. So in this problem I had the roots, let me write that right here, I didn't write that. I have the roots 3 plus I, 3 minus I, -3, 2, and 3. So those are my 5 roots. This is the way that I would write my factors. So my factors would be x plus 3, x minus 2, x minus 3, x minus 3 plus I, and x minus 3 plus I. I'm sorry, x minus 3 minus I, and x minus 3 plus I. Okay. Alright, so then our last problems are, what if I gave you the zeros and I want to know what the polynomial is? So here I said I have a polynomial of degree 3 and it has the roots 1, 2, and -3. So I can write out my 3 factors and then I just start foiling it out. So I'm going to FOIL out the first 2 and I end up with x squared minus 2x minus 1x plus 2. Clean that up, and now I'm going to FOIL that or distribute that in with the x plus 3, and I end up with a problem that looks like this. So that one wasn't too bad. You can also check this in your calculator by putting the first problem in your calculator and your answer in the calculator, and you should get the same result. Alright, so the next one's a little bit more involved. So this one, I have a polynomial with degree 3. One of the zeros is 4, and one of the zeros is 1 plus 2i. Well, if one of the zeros is 1 plus 2i, the other zero is 1 minus 2i. So here's my 0 of 4. Now when I work this out, I'm going to distribute out the imaginary roots first. So this imaginary root became x minus 1 minus 2i, and this one is x minus 1 plus 2i. So I start foiling that out. X times x is x squared. X times 1 is -1x. X and 2i is 2xi. And then I have to do the ones. 1 times x is -1x. 1 times 1 is 1. I left that out at first. 1 times 2i is -2i. Sorry. -2i times x is -2ix. -2i times 1. -1 is +2i. And -2i times +2i is whoops, that should be 4i squared. Which ends up being a +4. So I think I have a little mistake in here. So then I'm going to get x squared minus 2x, and then the 1 and the 4 become 5. And now I'm going to FOIL this out again. So I'm going to get x cubed, and I'm going to get minus 2x squared. This should be 5x now. And then I'm going to get -4x squared, I'm going to get 8x, and I'm going to get -20. And then one last step is to combine all my like terms, and I will end up with a -20 here instead of a -12. So I hope this helps.